Welcome back, students. In this video, we're going to look at two reactions that are very connected to one another, a halogenation reaction and a halohydrin formation. We're going to start first with a halogenation reaction and look at what generally happens, and then as we look at the mechanism, we'll figure out why the stereochemistry is the way that it is. In a halogenation reaction, you're going to start with an alkene, and then when you add a halogen, like chlorine, to the alkene in some inert solvent, like carbon tetrachloride, you're going to see two halogens add across the pi bond, so one to one side and one to the other. Most of the time when you go through these reactions, you're going to see chlorine and bromine being used because fluorine is too reactive and iodide is not reactive enough. Sometimes you might also see no solvent listed. Other teachers may include an inert solvent like this one, carbon tetrachloride, that isn't going to participate in the reaction. Let's look at the stereochemistry of this reaction by considering the mechanism. This is going to end up adding two halogens opposite one another. So that's your anti-addition, where your two groups are adding from opposite faces of the pi bond. When we consider this, we want to start with our alkene attacking the halogen. And when this happens, the halogen also attacks the alkene. So a pair of electrons from the alkene attacks the halogen, and then this bromine-bromine bond breaks. Now, this is really difficult to draw, this next part, so I'm going to do the best that I can and maybe even draw it two ways. So what's happening here is you have a bromine that is now attached to both carbons. That bromine is going to have a positive formal charge. When we draw this ring, it's called a brominium ion. When we draw the brominium ion, the problem with the way I've drawn it right now is everything looks to be in the same plane, and it's not. So if the ring is my hand, then the brominium ion is either pointing slightly up or it's pointing slightly downward. And that makes a big, big difference in the stereochemistry. One way to show that this bromine is not in the plane of the ring is to include some wedge and dash bonds. So we would maybe call them both wedge. You could also call them both dashed. And they're the same compound, right? If I ended up drawing these both wedge or both dash, I'd be drawing the same thing, so I'm just going to pick one. So this is going to show that the bromine is kind of flipped up. The reason that this is important is because now you have bromide ion in solution from when you expelled it here. And that bromide ion is going to be your nucleophile, and it's going to attack the electrophile. So where's the electrophile? Well, these carbons right here are your electrophilic carbons. Why? Because you have a halogen that's positive. So that halogen is going to pull electron density away from those alpha carbons or the carbons that the bromines are connected to, leaving a lack of electrons, which is a hole. So that is where your nucleophile is going to attack. The key to us having a discussion about how the bromine is not within the plane of the ring, it's pointing upward, is the fact that this bromine has a boatload of electron density around it. It's got a couple of lone pairs. And when you would consider the fact that your nucleophile also has a bunch of lone pairs, think of it like two north ends of a magnet. They come together and they repel. They don't want to be anywhere near one another. What that means for us is the second bromine, the one that's behaving as a nucleophile, is going to come in the opposite side of the bromine that's attached to the ring, because otherwise their electron groups are going to get too close together and repel each other. So this is going to happen. We're going to come in from the opposite side, and it can attack either carbon, right? I'm just showing the one that's easier to draw an arrow to. And once we have the bromide ion attack this carbon, this bond needs to break. Those electrons go up onto that bromine. And when that happens, the positive charge goes away because now the bromine has everything it needs. And the way that we would draw this is that first bromine was wedge, and it'll stay wedge. And that second bromine that's coming in is coming in from the opposite side, so it is dashed. Now, you always have to look out for enantiomers. You need to look at this and say, is the other enantiomer possible? Yes, it is, absolutely. Because you could have had attack equally from this carbon, or you could have attacked this carbon, right? So either one you could have attacked. And that means we're going to get a mixture of products. We're going to get both enantiomers, a racemic mixture. This is an area where it's really important for you to have that background in figuring out if two compounds that you've drawn, if they're enantiomers or if it's playing a trick on your eyeball and they're really the same product. And I find that a lot of students, once they get past that chapter, they'll look at these and go, no, those are the same. They are not. These are enantiomers of one another. And label this a racemic mixture. Now let's look at a sister reaction of this called halohydrin. The halohydrin reaction is remarkably similar with respect to its mechanism. The difference is going to be that instead of having an inert solvent, what you have is water. And water can also behave as a nucleophile. So water is going to end up being your nucleophile in that second step. Let's look at the stereochemistry by considering the mechanism, and then we'll look at the regiochemistry. So same idea as before. What's going to happen is your pi bond attacks the bromine attacks the pi bond, this one goes away, and you have that brominium ion now. Oops, don't put that pi bond in there, that's gone. And remember, these bonds could be wedge or they could be dash, and it doesn't matter because it gives you the same product, right? Whether they're wedge or dash, we'll put in our electrons, we'll put in our positive charge. Here's the difference. Now in solution, what you have is you have bromide ion running around, but you also have water. Let's look at why water is going to behave as your nucleophile instead of the bromide ion. In this case, it has completely to do with probability. You just have more water molecules than you have bromide ions. For every alkene that makes a brominium ion, and remember brominium ion is the fancy chemistry word for this thing, you only have one bromide ion. So these two are in a 1-to-1 ratio. Whereas when you add water, remember that 1 liter of water contains 55 moles of water molecules. So in 1 liter of water, you have 55 times 6.022 times 10 to the 23rd molecules of water. That's a lot of water. Now, I'm not saying you have a liter of water here, but even if you have a small amount of water, you actually have an incredible amount of water molecules. So it's just more likely, it's more probable that your water is going to behave as your nucleophile. Could the bromide ion do it? Yeah, but that thing's going to be surrounded in water much more thoroughly than it is going to be surrounded in bromide ion. So your water is going to be what comes in and does the attack and opens up that brominium ion. When this happens, you're still going to get that anti-addition because your water is your nucleophile, has electron density. Your brominium ion has a big old bromine with electrons around it. They don't want to be anywhere near one another. So the bromine is going to be on one face, and the water is going to come in from the opposite face. And that's why we're seeing this anti-addition. So your water comes in, it attacks, and remember, it still has both protons attached to it. Now you have to get rid of one of those protons. And in order to do that, you have to use the best base that's in solution. So which one's the best base, water or bromide? I bet you're thinking bromide right now, and it's not. Water's the better base than bromide. How do I know? Well, bromide's the conjugate base of a strong acid. Hydrogen bromide's one of your 7 strong acids, or 6, depending upon your general chemistry teacher. So water's going to be what comes in and pulls off that extra proton so that we end up with, oops, there we go. We end up with an alcohol instead of this thing that's called an oxonium ion that I like to call bound water, because who's going to remember oxonium ion? Great. Now remember that you should be drawing both enantiomers here, because there's an equal probability that the water could have attacked this carbon that I'm highlighting in blue in comparison to this carbon that I highlighted above it, which means that you're going to get a racemic mixture of two products here, where your bromine could be dashed and your water, not your water, your oxygen, your OH, can be wedged. Right? So this is racemic. Now let's dive into regiochemistry. If you have an asymmetrical alkene, we need to be able to know, is the bromine or the OH going to add to the more substituted side? And it's going to be that the OH adds to the more substituted side. So let's draw that. So if we had this reaction, our bromine would go less substituted, our OH goes more substituted. Let's talk about why. I'm going to split these ideas. Over here that I'm highlighting or boxing in yellow is my brominium ion. My brominium ion, remember, has a bromine that has a positive charge. That bromine is pulling electron density its direction. So it's pulling electron density from here, and it's pulling electron density from here. That's leaving partial positives on those two carbons. Well, which carbon's better able to stabilize the partial positive? Well, the one with more groups attached. So the one that's better able to stabilize the partial positive is the one that's going to have the more stable transition state. That's an ugly arrow. Let's try that again. So the nucleophile is going to attack the more substituted carbon, which is going to open this up. Right? And that is why you see the OH adding to the more substituted side. Let's wrap up. In this video, we looked at two reactions, halogenation and halohydrin formation. For halogenation, we saw that we added two halogens across the pi bond. We usually stick with chlorine and bromine. This produced anti-addition, where the two halogens added from opposite faces, and you have to make sure that you're watching out for enantiomers. In your halohydrin formation, you added a halogen plus an OH across the pi bond, where the OH added to the more substituted side. Again, we saw anti-addition, so the OH and the halogen added from opposite faces, and again, watch for enantiomers. Thanks so much for watching. This is Katoni signing out.